State in terms of force the conditions necessary for an object to move in a circular path at a constant speed. So, when you have circular motion, if an object is moving in a circle at a constant speed, the resultant force must point towards the center of the circle, which would be the answer to part 1. So if you were to have, let's say, here is the Earth, and then you have some satellite over here orbiting around the Earth with a constant speed, the force points towards the center of the Earth. In this case, that's the only force. It's the resultant force. That's the gravitational force that causes that circular motion. And for part 2, explain why this object is accelerating, state the direction of the acceleration. So the acceleration will act in the same direction as the resultant force. So from Newton's second law, acceleration and force are in the same direction. Why is it accelerating? Acceleration is the rate of change of velocity. Velocity is a vector. So although the speed is constant, the magnitude of velocity is constant, its direction is changing. And if its direction is changing, then that means there must be some kind of acceleration. That acceleration causes the velocity vector to turn. Its direction changes, but its size doesn't. And then for part B, a satellite moves in a circular orbit around the Earth at a constant speed of 3,700 meters per second. The mass of the Earth is 6 times 10 to the 24 kilograms. Calculate the radius of this orbit. So we can equate the gravitational force, because we have circular motion, we can equate the gravitational force to the centripetal force. You have two options for the centripetal force equation. You can either use mv squared over r or m omega squared r. In this case, I've used mv squared over r because we're given the speed. We're not told what the angular speed is, so although it is also equal to m omega squared r, this wouldn't be as useful as this version of the centripetal force equation. So using what we have here, we can cancel out a factor of r, we can cancel out a mass. The mass that cancels would be the mass of the satellite. And we know that because for this expression that we have over here, the mv squared over r, this is the centripetal force that the satellite experiences. This must therefore be the mass of the satellite. It's the mass of the thing that's moving in a circle. So those cancel out. We're left with the mass of the Earth, which is good because that's the only mass that we have. And then we can rearrange this for r. So switch the r and the v squared, and we end up with r is equal to gm over v squared. Type this into the calculator, and we end up with 2.92 times 10 to the 7 meters. For part C, in order to move the satellite in B into a new, smaller orbit, a decelerating force is applied for a brief period of time. Suggest how the decelerating force could be applied. So, if the spacecraft ejects some mass in the same direction in which it's traveling, so in the forwards direction, that will apply that decelerating force. If the spacecraft exerts a force to push some mass, like some gas for instance, if it has a rocket that faces forwards, that pushes gas forwards, the rocket or the spacecraft is exerting a force on that gas in the forwards direction, and the gas exerts an equal and opposite force on the rocket in a backwards direction. So like a really bad diagram of that. Here's your spacecraft, here's some random gas. The spacecraft pushes the gas forwards, and then the gas pushes the spacecraft backwards with an equal and opposite force. And that's how it can experience that decelerating force. And then finally, for part 2, the radius of this new orbit is 2 times 10 to the 7. Calculate the speed of the satellite in this new orbit. So we can use the same equation from before, equate the gravitational force to centripetal force. For a lot of circular motion questions, or for a lot of gravitational fields questions that have circular motion or circular orbits, you often want to use or equate gravitational force to one of the centripetal force equations, and then rearrange for whatever we're trying to work out. So in this case, we're trying to work out what v is. Again, a factor of r cancels out, the mass cancels, the mass of the satellite that is, and then we end up with square rooting both sides, v is equal to root gm over r. Type this in, so the radius is what we have over here. The mass is what we had before, 6 times 10 to the 24. Put those in, and we end up with the speed being 4,470 to 3 sig figs.